The particular application of this topic is for rapid additive manufacturing in space, aviation, sea, and land. And particular scenarios include microgravity and strong random vibration. This is a video, space station, and 3D printing has been applied last year in space station. And this basically is the same technology as used by NASA, FDM type of methods. As you can see, it's pretty slow. And another scenario, as I mentioned, about strong random vibration. Here is a video. Okay. If you want to print something on a boat, at a boat, for example, it's going to be tremendously difficult because it's a strong random vibration. Another application is, on the land, can we print something, 3D print something over here? Again, strong random vibration. Now, another very important thing is about rapid manufacturing, which means it must be done within a short period of time. And of course, the typical ones, the technologies are currently commercially available, has been applied in fabrication, for example, Adidas shoes. And the liquid is used and using UV cross-linking. Another technical that is called volumetric additive manufacturing, as illustrated here. Here, two beams are used for cross-linking instead of just one single beam. Now, can we do that in solid instead of liquid? Because previous ones, they all use liquid and cross-linking. And this one, is made of this kind of glass. And that's actually solid state processing technology. Okay, here we go, a video. It's a piece of glass, it's solid, and using laser decoration, engraving. So they'll come out with shape inside of it. Actually, the purpose of using laser is to generate cracks inside of it so that we can see the feature we want to embed in. Here I have a small video to demonstrate volumetric additive manufacturing in solid state instead of liquid. So we have a mask placed on a solid piece and I cross-link it, and then turn that by 90 degrees because it's solid. And then using another mask, cross-link again, and in the end, we need to remove the uncross-linked part, and the remaining cross-linked part is what we want. For the real experimental demonstration, videos here. There's a videos about this. The first one, this one, is in YouTube, and this one is in Ucrew. Now, let's simulate another scenario. UV cross-linking using dual laser beams. Okay, we have two beams. One UV beam is flat, another is a line beam, so that we can move it gradually, and in the end, it is in solid state, okay, so that is solid, and we don't, whenever there's a gravity or non-gravity or microgravity, or if even there is any severe random vibration, doesn't matter, and later we can remove the uncross-linked part, and the remaining, in this case, is a solid spiral spring. This is cross-linked part. Okay, so basically it's the idea of solid state additive manufacturing. Now I have an example to demonstrate this concept. We use a particular type of gel that's called thermal gel, and different from other materials. This material has a unique feature of cooling melting instead of heating melting, as demonstrated over here. This is actually a video. This gel is solid, and then upon cooling to 4 degrees, you can see it become liquid, fully liquid, so that we can, after cross-linking, we can actually remove the uncross-linked part upon cooling. Now, let's demonstrate the concept using one single mask. We have the solid gel, okay, without cross-linking at room temperature. We place a mask on the top surface of it, and then use UV to cross-link it. And after cross-linking, we cool down the whole thing, and the remaining is what we want. I'll have a video to demonstrate this whole process using a particular type of thermal gel. And we use only one mask. For the case that we use two masks, I have a link, you can refer to that. Okay, now it's liquid because it has been pre-cooled. And after a while, at room temperature, it becomes solid. Okay, so it's solid cross-linking. The next step, we place a mask on the surface. It's an S-shaped mask. And wrap it underneath UV light for cross-linking. This is an old version of the composites. Now we can speed up the whole process. It could be much faster. Now we remove the mask. You can visually see the S shape there. This part has been cross-linked. The rest is solid. The rest is solid, but it's uncross-linked. Now the whole thing is in solid state. And then we can cool it in 4-degree fridge. And then we can take the cross-link part out. You can see the shape actually is distorted. So we need another important phenomenon, shared memory effect, in order to make sure that what printed is precise. Okay. Now, the case we demonstrate in the previous slides is gel, which is soft. Now, can we achieve that using hard polymer? Yes, it is possible. As we all know that between thermoset and thermoplastic, two typical types of polymers, they're actually another type of special polymer that is called bitumen. And the particular feature of this bitumen is that it has a reversible cross-linking instead of fixed cross-linking or without cross-linking, as in thermoset or thermoplastic polymers. And the particular feature of this reversible cross-linking is shown over here. This is the percentage of cross-linking, and this is temperature. So that if you heat up, the cross-link starts gradually disappear. Until over here, high temperature, there's no cross-link at all, becomes thermoplastic. Upon cooling, the cross-link starts gradually reverse back to its previous condition, and therefore becomes thermoset. And so you may wonder what's this for, and how this can be used in 3D printing. Now, bitumen. This is a commercial bitumen, okay, commercially available bitumen, and this is the DSC differential scanning calorimeter results in 2 thermal cycles. So this heat flow and this is temperature. Now you can see within this range, upon heating to this range, whatever in the first cycle, second cycle, around here, about 70 degrees, it fully melts. Okay, this is according to DSC. But according to DMA, dynamic mechanical analyzer, this is a strain and this is temperature. You will see that upon heating to this range, the strain rather periodical within this range. And okay, if you heat up the higher temperature within this range, 90 degree over here, which means it fully melts. Okay, it fully melts, but it still maintains original shape. You can see the strain upon cyclical loading. And even heat up to this part, about 100 degrees, it still maintains shape, which is well above its melting temperature. You refer to DSC results. And the material only starts to flow over here, which means well over 100 degrees, 107, it starts to flow. Okay, so melting, that means it's easy to flow. You need to heat up much higher temperature in order to make it possible to flow, because all the cross-link has been destroyed. The material becomes thermoplastic. And this is a very important feature. We can cross-link bitumen, and then we can use this feature for 3D printing in solid state. Now, the very important thing is that the material must be transparent, because if it's not transparent, we won't be able to use photo cross-linking. Over here, you can see that it's brought before cross-linking, and this part is heated area. You can see two different angles of view. You can see here and here, the material is transparent. So it's just right for photo cross-linking or photo-induced heat cross-linking. So after cross-linking, we have another feature, as mentioned, to ensure good accuracy of the printed item. So this is the original shape after cross-linking, and this is after programming. Basically, you disconnect, separate the cross-linking part and the uncross-linked part. You need to use the shared memory effect. So after programming, the material actually distorted. But later on, you can heat up, for example, using heating activate shared memory phenomenon. So it's able to fully recover its original shape. And okay, a very important thing is that is this material hard? Okay, not so soft. This is stress versus strain relationship. This is a stress versus strain relationship of the cross-linked material. The slope This basically is Young's modulus is about 1 gigapascal. So this is hard too. Now, summary is another video. We propose a concept that is rapid 3D printing on space, air, sea, and even land missions. See, for the applications, microgravity, random vibration, or on land. Solid state, you can use two beams to cross-link. And later, I didn't manage to get any gravity force, gravitational force. And you can see severe disturbance doesn't matter. And later, you can use a way to remove the uncrossing part, and the remaining is the crossing item what we want, and we can utilize the shape memory effect to make sure that the accuracy, good accuracy of the printed item.